Yes, sir.
Yes, sir. So I'm just taking direct application of momentum equations and continuity equation in the cylindrical coordinate. So this is actually the problem here. We are taking the first case study. So that's you have the fluid inside this. This is the pipe actually. So inside this pipe, the fluid is flowing, and for time being, you can say that pipe is horizontal, but it can be inclined to any directions without any problem. So for timing, let's say it is horizontal and z axis is parallel to the means axis of this particular the cylinder. So and r coordinate is the radial the direction of that. So that is r side. Theta is just to make the complete circle actually. So that is the theta side. So theta would always be means perpendicular to this side. So r and z. So you have these three coordinate in this particular way, and fluid is flowing only in z directions because what you have here that boundaries are completely means non-perforated, or you can say it is completely smooth cylinder without any holes on the boundaries something. So a smooth pipes, in that case what you say, there no flow in radial direction, so only flow would be in axial side. Fine. As per Yes, the sir. nomenclature thing, your G always act vertically downwards. So based on that, you can say that what component of G would act in the direction of the flow. So that's another part. And velocity in z direction is being considered here, either vz or you can say w. So that's way. So in that way, so as you see that if you want to do the cell balance for that, means suppose a person wants to do with the help of the cell balance. So for that particular part, you take the small differential element of this particular section of this pipe, just like this. You have taken this, just increase of this delta r and delta z, and just do your mass balance and force balance as we did in case of your rectilinear coordinate. I hope you can recall what we did for the rectilinear coordinate. Correct or not?
Yes, sir.
So that way you just try to do those derivations, momentum and mass balance, and if somehow if you are not getting, you can take the help of the notes which I will just share to you. So because the motion here, so we can say the problem statement that it is a Newtonian fluid is flowing through a pipe in the laminar flow, and we are putting a constant here. Fully developed flow means do you know now what do you mean by fully developed flow?
Yes, sir.
Can anyone tell what is fully developed flow?
Sir, it is a region where the flow of fluid, where the velocity profile does not change with the downstream distance.
Actually, voice is breaking. I can't hear properly. So fully developed means that velocity is no more the function of that space coordinate in the direction of the flow. That's the meaning of fully developed means this Vz will not be any no more would be the function of z. Z is the direction of the flow. It means del V z upon del z would be equal to 0. So that is the definition of fully developed flow. However, it can change with the other direction. That's not the concern, but no change with the direction of the flow only, right? So for that, second term, we always calculate all the time what is the pressure gradient and del P upon del Z term. So because this is confined flow through a confined geometry, so you always need a pressure. Without that, it won't flow actually. In case of horizontal case, horizontal or vertically upward, so you have a pressure at inlet is P1, at outlet is P2, and corresponding coordinate of Z1, Z2 are 0 and L. So you can calculate what is P1 minus P2 based on 0 minus L here. So you are getting minus delta P by L. Delta P is called pressure drop. Now there one more term del P upon del Z. So you can calculate from there, integrate that, and then you are getting from here that del P upon del Z is the nothing but is minus delta P by L. Okay.
Yes, sir.
Now Uh, this is your continuity equation or mass conservation part. Once you will do the derivations, is available in your transport phenomena book at the back also. So for that, if you will apply your continuity equations, then you have here del rho upon del t, 1 upon r del r rho v r upon del r, plus 1 upon r del rho v theta upon del theta plus del rho v z upon del z equal to 0. So now you are putting what your constraints are. So you have here steady state, so the nothing is the function of time, and then uh, here you are cancelling this term because the VR is 0 because no flow in radial directions. So the velocity in the radial direction is the 0. Now, V theta, actually, is there any flow in theta direction? So this is also is getting cancelled by two means that the diameter of the pipe is not changing, and means you have here axisymmetric flow means nothing is the function of theta. If you are at a particular r, either you calculate velocity at theta 10 or 100 or 200 or 360. At all points, your velocity magnitudes is not the function of theta only, right? As far as you are at a particular radial distance from the center. So this is from axisymmetric flow, or you can say that if you are talking about totally one-dimensional flow, it means you are considering that V are equal to 0 or your B theta is also equal to 0, right?
Yes, sir.
Yes, sir.
Last term, either you can cancel it from here, or if you are not cancelling, it is automatically coming equal to 0 from here. So if you say by putting all these constant here, that V are equal to 0, V theta, so from here it's coming that del V z upon del z equal to 0. It means that your Vz is not the function of z only. Or you can put a constraint from your side that fully developed flow in z directions. From there also you will get del V z upon del z equal to 0. Fine.
Yes,
This
sir.
part you just leave that how to find that g cos theta something. So just leave it here for time being. R momentum balance you can apply because generally we have to means apply all the momentum balance in all three coordinates, and once you will simplify that, you will come to know that something will come from each momentum balance. So this momentum balance is practically giving you the del P upon del R, how the pressure will change with respect to R coordinate, because pressure will change as you are going up and down inside the fluid only. So from here the pressure is coming, nothing but is P is coming rho g R only, rho g sin theta into R. So how much component of G would act in that particular directions, R directions, and then this would be always a function of theta because you are keep on changing the orientation. Sometimes you will have totally in vertical side, some may be in a particular theta orientation. Therefore, you are taking what would be the g in corresponding direction. Therefore, you have put a constant here, g sine theta. So this would always tell what would be the value of g at a particular theta orientation. So that's the another part. Same way you can do the momentum balance in theta directions. So if you will calculate that, you are ending up with the same thing as you got previously. Also previously also you got minus rho g r sine theta, and here you are putting a function of z. So it may change along the axis of the pipe. Now come to this main part. The main part is the momentum balance in the direction of flow only. So this the main direction of the flow was the z momentum balance, and this is the z momentum balance equation. These equations would be provided to you in your question papers. So if you can remember them, well and good. If not, these would be provided to you because sometimes we cannot by heart everything. The main part is you should know application part of that. So this is your Z momentum balance. Now you are cancelling here the term. First term you are cancelling del B Z upon del T by putting a constant here, steady state flow. Second term, you are cancelling this VR because you are considering the flow is totally in Z direction. So you are considering you are putting your VR and B theta you are putting equal to 0. So second and third term is getting cancelled. Now here del Vz upon del Z you are putting equal to 0. One thing it came from continuity equation which you did previously. Also you can put it here the flow is fully developed. So again that way also del Vz upon del Z will get cancelled. Okay. Now
Yes, sir.
this side you have this your pressure gradient minus del B upon del Z. You have rho g z component, and these are your all your viscous stresses actually. So that would be from here. Now from in this only the you are second term you can rewrite it here del upon del theta again del b z upon del theta. So this term is getting cancelled from the condition of axisymmetric flow. Your velocity will not change with respect to theta coordinate because the your cross section is uniform. So uniform cross section is the radius is not changing at a particular position z only. However, it can change from different z to z, but at a particular z, it is not a changing with respect to theta. So in that way, that flow is called axisymmetric flow. So for that condition, you can cancel the term del b z upon del theta. This second term is getting cancelled del b z by putting a condition of fully developed flow. So you left with only first term only. So if you have first term here, so from here you can write your velocity is totally the function of r. So you can rewrite your all partial derivatives in terms of total derivative because your vz is purely a function of r only. It is not function of theta. It is not the function of z. So this you can rewrite, arrange it. So finally, you are ending up with this means equation del upon del r bracket r del b z upon del r equal to minus delta p upon mu l into r. So this is the equation you will always end up in all means calculations in cylindrical coordinate, or you can go slightly back, maybe this one. This equation. Now this is nothing but is your shear stress. So if you can write it in terms of shear stress, so Newton's law of the viscosity, what does it say? That mu is tau r, tau rz is What is tau Rz? Is mu del Vz upon del R. Okay.
Yes, sir.
Yes, sir.
So that is the shear stress part. So you can write that. So this would be always come to you. So let's say I can take this marker. Maybe it may help to you. So this would be the equation which you will always end up. Okay. So that you can use for any type of fluid, or because you can rewrite this in terms of that means the stress this particular term, and then this equation can be used for any type of fluid, because then you are not putting a constraint whether it is the Newtonian fluid or power law fluid or Bingham fluid something. If you can rewrite this equation in terms of shear stress, fine.
Yes,
Yes, sir.
So now you have this equation that need to be solved, so you can integrate that. So before doing that, convert this partial sign to the total, because Vz is only the function of R only. So if you will integrate first time, you are getting a constant C1. If you will integrate second time, you are getting a constant C2. Now these constant need to be evaluated. So for that, you need something. What are the boundary conditions? So if you see the figure, so for that case, what are the boundary conditions? What would happen at r equal to 0? At r equal to 0 means you are at the center. Your velocity would be the maximum, right?
Yes, sir.
Or so in that case, your shear stress must be equal to minimum. So or for the maximum and the minimum condition, your del Vz upon del R term must be equal to 0. This is the condition of the maximum or the minimum. That is one thing. So velocity means the maximum, or shear stress must be minimum. You can say in worst case could be equal to 0. And for minimum or maximum condition, your del Vz upon del R term must be equal to 0. So that is the one condition at the center. Second boundary condition would be at R equal to plus minus R, or you can say that once you will reach to the surface of the cylinder, so that is R, full R, capital R. So R equal to capital R, what would be your condition? Your velocity would be equal to 0, because it is no slip condition, because your pipe is stationary, right?
Yes, sir.
So these are the two boundary conditions, and those need to be used to evaluate that. So let's say for this, the time you will put R equal to 0 in this particular term, equation number 3, or let's say equation number 2, what will happen here, that ln R term would become infinity. But your things are finite. You are solving a question because your shear stress, because if you are calculating from here, so this can be written in terms of shear stress also. So from here the things would come infinity. So to make it finite, you are forcing the constant C1 should be equal to 0 to make this particular term finite, because the infinite thing cannot be possible in this particular case. So for that, you got your C1 constant is 0. Now you have the another boundary condition, that R equal to plus minus R at your boundaries, your Vz equal to 0, which is your no slip condition. So you can substitute that here in this equation number 3, and then you can calculate your constant C2 expression. So you can put here 0, you are putting here R, so you will get expression for your C2. So for that, if you will put that, your C2 expression is coming that delta P R square upon 4 mu L. Now for that, now you have the constant, substitute that back into the equation number 3. So you will get your velocity expression is Bz equal to delta P r square upon 4 mu L 1 minus r square upon r square, right? Now, if you want to find what would be your maximum
Yes, sir.
velocity, just substitute at this small r equal to 0. It means you are at the center. So this term would be your maximum velocity. Okay. So this is your maximum velocity. Now, to find the maximum velocity for a given fluid, something or you need not to perform any practical. You can just measure the delta P on both the ends. Length of the pipe is always known to you. Viscosity of the fluid is also known to you. Radius of the pipe you already known to you. So you can calculate what could be the maximum velocity if I will apply this much pressure drop. Or you can say I want this much the maximum velocity. You can calculate this much should be my applied pressure drop at both the ends, right? So you need not to perform any practical. You can come to know from here what could be my theoretical values just to get that particular velocity or that much pressure drop, right?
Yes, sir.
Yes, sir.
So you got from here velocity, then after that you can calculate the flow rate. Okay, so the flow rates, then you can calculate from shear stress. So shear stress you can write tau rz equal to mu del b r del b z upon del r. So you can substitute here. So the previously you already have the expression of bz now. You can differentiate this. So you can differentiate this. You will get the this expression of del bz upon del r, or you already have the means expression of del bz upon del r is this only minus delta p r upon 2 mu l. C1 constant was 0, so you can cancel this term. So you will left with the all this term you can cancel. So you left only this. So this is your del bz upon del r. So if you are calculating shear stress at the center, r equal to 0, so that term will get cancelled. So therefore shear stress at the center would be 0. If you are calculating at the wall, r would be here plus minus r only, right? Either on top side or on bottom side, correct?
Yes,
So
sir.
in that way, you can calculate your shear stress. So shear stress expression is coming minus tau rz is minus delta p upon 2l into r. Okay, so shear stress profile is linear. So linear means it will look like or something like that. If you are plotting with respect to r here, and this is your r coordinate here this way. So your shear stress would look like this only. Fine, so this would be your center. Here is things coming 0. So let's say you are going on top side at top surface. You are putting R is capital there. So one side, this, sorry. So this magnitude is coming in the minus. So it means this direction need to be changed or something like that. So that need to be taken care, because if you will put here r value positive here, this would be this thing is coming negative, right? So therefore this would be in this side. If you are putting r value the negative one in the bottom side, this would look like that. So this would be your shear stress profile. Now, if you want to calculate the force applied on the fluids, that would be different, because as you will go on top, this magnitude is coming minus, right? Hello?
Yes, sir.
And here, what would be the plane? So, if you draw the perpendicular, that perpendicular it will go to minus r side. So perpendicular will go to the this side. So this would be minus r plane. So both are minus sign. Therefore, your shear force would be in plus side. So it means it makes sense. It will try to drag the pipe into the direction of the flow. Same thing for bottom side. So if you are bottom here, your r is plus, this magnitude is coming minus. And what about the plane here? So in this case, if you are at bottom, your plane would be this plus r, because perpendicular here drawn would go to the plus r side. So therefore, both are plus. Plane is plus, magnitude is plus. Therefore, your shear force would also be in plus side. So in both the case, your pipe would be dragged out by the fluid only. If somehow you are getting at top force is plus, bottom force is minus, it means net force on the pipe would become zero in that case. Okay.
Yes, sir.
Now let's say you want to calculate the flow rate. So flow rate expression for u are same. So you can calculate q is v dot dA. So you have v is velocity. Expression dA in the cylindrical coordinate is r dr d theta. So theta is changing 0 to 2 pi if pipe is fully filled. So if pipe is not fully filled, let's say you have half filled pipe. So theta would change from where to where? Suppose you have half filled pipe. So theta would change from where to where? Hello? Any answer?
So 0 to pi?
No, 0 to minus pi, right? Because you are going this side, because if it is half filled, oh, so in that case, bottom half is filled, not top half, right? So if
Yes, sir.
you have to go to the anti-clockwise, right? So in
Yes,
case
sir.
of half filled, you are in bottom side, so your theta would go 0 to minus pi, right? So because top half you cannot fill, because you cannot hang the fluid on top, right? So in that case, 0 to pi, otherwise it would be 0 to minus pi. So in both the cases, your sign would change, and based on sign convention, you will come to know what is happening there. So sometimes people just take a mode of that and calculate it, because they are only interested in quantity. They are not interested in sign. So you have velocity expression, substitute here. Now theta is 2 pi, so theta is not coming in velocity side. So you can integrate theta directly. So you can just put a 2 pi here. Now multiply with RDR inside, integrate it. So you will get this expression, and finally you are getting Q is pi R4 delta P upon 8 mu L. So this equation is known as to you is Hazen-Poiseuille equation, the pressure drop in laminar flow in smooth tube or pipes. This you can rewrite it to in terms of let's say diameter. So you will get expression of delta P is 128 q mu L upon pi d4, right? So that is another form of Poiseuille equation, right? Correct?
Yes, sir.
Yes, sir.
You can also rewrite this in terms of velocity. So you can write at the place of q, you can write v into a, right? Correct or not?
Yes, sir.
Yes, sir.
Yes, sir.
Then area you can write further pi d square by 4. Rearrange the whole thing, then you can get the means another expression for delta p would be that that 64 upon re into f L upon d v square upon 2g term. So that term also can come from there, and then you will get that is the Fanning friction equation also from here. So that you try to do it. you can get it. Okay, so now you can calculate based on flow rate, you can calculate average velocity. So average velocity just Q by A. So you got the Q from here, area from here. You can integrate here 0 to 2 pi, 0 to r dr d theta. Or if pipe is fully filled, you can directly write the area of cross section is pi r square, right? So based on that, you got the average velocity. So average velocity is coming by this r square delta p upon 8 mu l, which is half of maximum velocity. So you already know the maximum velocity expression. So maximum velocity expression, here you have the term 4 mu l. Here you are getting 8 mu l. So in that case, the average velocity is the half of maximum velocity. So most of the time, when we do the calculation based on the average velocity, we are making around error of 50%. Correct or not?
Yes, sir.
So the based on maximum velocity, things need not to be calculated, and average velocity is some idea is okay. So most of the time, you don't know what is the maximum velocity also. So people do all calculation based on average velocity part. It also matters that what should be the diameter of the pipe. So let's say you have very thin tube. So in that case, this maximum velocity, average velocity variation will not be that much high compared to a large diameter pipeline. So in that case, there would be huge variation between maximum velocity and average velocity. And then you can rewrite the things in, that your velocity expression would be maximum velocity times this, or you can write here delta p r square upon 4 mu l, because that is the expression of maximum velocity. Now once you have maximum velocity, average velocity, what else do you need to find? You need to calculate what should be the drag force by this particular fluid on the pipe. So how would you calculate drag force? Shear stress multiplied by area, right?
Yes, sir.
So shear stress expression you already know from here, that is the shear stress minus delta P upon 2L into R. You want to calculate drag force, so this would apply on your entire circumference to multiply by area. So if you want to calculate at wall, so this R would become capital R, area would become 2 pi RL, right? That would be entire circumference on which this shear force would act, right? So you are multiplying by R here, here you are putting the 2 pi RL. So 2 and 2 will get cancelled, R become R square, L would also be cancelled. What would be your final expression would come delta P into A, right? Because you are getting the term now pi R square, right?
Yes, sir.
Hello? So that would be your drag force applied by the fluid on the pipe. And now, what would be the benefit to calculate that? Based on that, you will calculate how much force should I apply on this particular pipe to keep it on hold at this particular place. Because once you have calculated that, based on that you can say what should be my clamp size or the tightening or bolt, because the pipe, the all pipes always are clamped, they are not kept and open. The reason is that you will apply this particular drag force or fluid flowing always have a tendency to drag it in the direction of the flow. So based on that, you can calculate this much force should be supplied by your clamps on the pipe in opposite direction of the fluid so that your pipe should remain as it is, right? Okay.
Yes, sir.
Now, so this means all about is your Newtonian fluid in a in a pipe. So what we have found here, we have found here velocity expression, we have found expression for shear stress, Velocity distribution you can calculate from here. How would it look like? Your velocity would come. What type of velocity would it come?
So parabolic
Any
profile.
idea? Yes, yes, it's parabolic because here you have power 2. So it would be a parabolic profile. Let's see if I can draw it. So this would be a parabol. It's not coming good one actually. So it should be parabolic, not like a corner and all this. So it would look like something like that. So don't make this way. So this is a parabolic the profile there. Now shear stress profile is the linear, and you got maximum velocity, average velocity, and the pressure drop calculation. So these are the only things which we always are concerned in case of transport of the fluid in a pipe. Okay. So anything, any doubt in this so far? Whatever we did.
No doubt, sir.
So similar way, you can try at home here. The next way there, because the most of the time we do heat transfer or some other part flow through annulus actually. So it happens in two ways. That one is when we do the drilling or drilling of, let's say we are making a bore or drilling of the petroleum petrol from this a petrol well. So what you have here, you always have a double pipe type of thing. Most of the time, people pass a hot water inside this the inner tube, and then it will go to the annular part, and your petroleum crude comes to the annular space upward. So that way, your petrol is being extruded, means taken out from the earth actually. So they always pass a hot water or the steam inside this, and outside of that, you got the flow. Same thing also you happen in case of your double pipe heat exchangers. So you have maybe a hot fluid or cold fluid inside the tube, and outside of that you have the different fluid maybe flowing with a different velocity. And you are also interested that how this velocity variation would happen, because it will impact your heat transfer or the mass transfer process, correct?
Yes, sir.
Yes, sir.
Hello? So this is the case where you have steady axial laminar flow in the annulus here. So in case of inner pipe, your expression would remain same as you did previous one. There would be no change as far as this fluid is not in contact. So this fluid is not contact. You have perfect boundaries at the inner surface. You have this one. This is the inner boundary, which is completely not in contact on the fluid. And this is one more is the outer boundary here. So you have two boundaries. Both the solution need to be solved independently, not so they will not impact the solution of the other side. So this side solution, inner side is same as we did previously. Let's say we want to do for the annular side. Annular side again, your things are same as we did in the previous. I will explain only you the boundary condition. So here your R coordinate is always from the center only. So center is from here, inner tube center, just like this. So you have two radius. One is the mean the radius of the inner pipe, radius of the outer pipe. So that is Ri and this is R naught. Fine. So what would happen here at the Ri also? Your velocity would be zero, because this is also the no slip condition. At r equal to plus minus r naught also, your velocity is also again the zero you have here at the outer pipe, correct?
Yes, sir.
Yes, sir.
So by applying these two boundary condition and previous expression is the same till here, your expression is same, this one. So by applying this is the equation need to be solved. You have two unknowns, two boundary conditions. Try to solve it here. Now this particular part at L and R thing. Now, because you are solving it to the annular part, you are not solving to the inner cylinder parts. So here, this at R equal to 0 condition is not at all valid for you. So there are no question here just to put at R equal to 0 because you are not solving, you are not satisfying any boundary condition at R equal to 0 because there is no R equal to 0 in the annular space, right? Here. Because here you have R equal to Ri or R equal to R naught only, correct? So you have
Yes, sir.
here these two unknowns, two boundary conditions. These are the two boundary conditions at R equal to R0, Vz equal to V0. At R equal to Ri, you can put plus minus if you want to put Vz equal to 0 again. So you can substitute these two boundary conditions and then you calculate your constant C1. Then after that, you will calculate your constant C2. Rearrange them, you will end up with the velocity expression that Vz would be equal to this expression only. Okay.
Yes, sir.
So some may end up here with the term here Ri, depend which equation they are using to calculate your C2. If you are calculating C2 from R01, you will calculate this term in terms of ln R naught. If you are calculating from here Ri naught 1, so you will get some term here Ri naught. So don't get confused from both the way, both the expression would be fine only. Because at last you are clubbing everything here, so you will end up with something here, something like that only. So I will just quickly end it here. So here you will get velocity expression. Now next part is your here flow rate, right? Flow rate expression is that's only Bz into 2 pi r dr d theta. So your d theta is full pipe is fully filled. So you just put 2 pi, only you have r dr. You already have velocity expression, multiply it by 2 pi r dr, integrate it systematically from here, and you also need by integration by parts this trick also here. So by doing that, you will rearrange all these expressions, and finally you will end up with your velocity, your volumetric flow rate would come in this particular format. R naught 4, Ri 4, and Ri minus this format. Try to rearrange it in this way. So you got velocity, means volumetric flow rate. After that, you can calculate expression for maximum velocity. For that, you need del B upon del R must be equal to 0 because this is the maximum condition thing. For maximum minimum, your first derivative must be equal to 0. So you already know the expression of velocity, differentiate that, and from here, you are getting this is the condition R. R is this one, and from here, this is the point where maximum velocity is there, which is coming closer to the inner surface, not at the midpoint of the annular. It is somewhere close to the inner surface. Okay.
Yes, sir.
Then you have effective diameter, or you can say hydraulic diameter. So you have here now two surfaces. So you can calculate 4 times of cross-sectional area upon wetted perimeter. Cross-sectional area for flow is this, it means outer area minus inner area. Wetted perimeter is the nothing but the perimeter of your surfaces which is in contact of the fluid only. So that is the outer perimeter 2 pi r naught. Inner also, because both the surfaces now in contact of the fluid only, right? So
Yes, sir.
based on that, you are calculating your hydraulic, the diameter is coming 2 times of R naught minus Ri. This, based on that, you will calculate the Reynolds number, and if this is less than coming 2100, then it is the flow is laminar, otherwise it will be treated as turbulent type of thing. Okay, so
Yes.
we will end it here today. So try to complete both the derivations.
Okay, sir.
Fine.
Yes, sir.
Yes, sir.
So if you have any doubt, you can ask, or you can ask in the next class.
Okay, sir.